Escape Chimp problem. Here we go. Supposed to have this one up before. I recorded the wrong thing over it. Now we'll talk about it. So this is our classic problem. Any textbook you're going to find it in. It's very common. It's usually a child walking away from a light source above them and how the tip of their shadow moves away from the pole. So we're going to be wondering a little bit about what the tip of the shadow moving away from the pole is. For in our case, our lucky chimp walking away. So let's get into it. A street light is at the top of a 15-foot tall pole. An escaped chimpanzee that is 5 feet tall walks away from the pole with a speed of 2 feet per second along a straight path. So it's basically saying we got a 15-foot tall pole with a light source. We got a chimpanzee that's 5 feet tall, so a third the height. Doesn't really matter in this problem, but 5 feet tall actually kind of does. We'll see. 5 foot tall walks away from the pole, and we know how fast she's moving along a straight path. So that's going to be some change in something later. That when anytime we see per unit in time, we're like, hey, that's a derivative. That's some sort of chain we're going to be popping out. And then the question is, how fast is the tip of her shadow moving away from the pole? So that's the question. How fast is the tip of her shadow moving away from the pole when she is 17 feet away from the base of the pole? I already got the when underlined on this one. This is about my 15th take, so I keep making mistakes. All right. Let's see. We'd probably want to draw a picture, wouldn't we? Let's get a picture going. Of course, I got something drawn out. Here we go. We got a little light source here on the left, 15 feet above. We got a 5 foot chimp walking away. She's jamming out. She's trying to get out of here. I would too if I was locked up in a zoo. We were given that she's walking away, so she's going this direction. She's going that way, and I've kind of labeled, like, we got to give some length for her away from the pole. From here to here, and I've already kind of labeled it down below. You can see is X. So if she's moving away with that movement, we know that that must be dx dt. And we had information on that, and that's 2 like feet per second, I think. I don't care. I'll look at it at the end. I'm not a physics person. This is math. Well, it kind of is physics, but let's just get back to the problem. All right, man. So we got the chimps moving, and the question really we're trying to figure out is how fast is the tip of her shadow? So like her shadow would be like right here, huh? That would be her shadow. Well, we want to know how fast the tip. So the tip right here is moving away from the base back here. So it's actually this whole length that we're going to want to look at. That's what the question is asking. It's not asking for what's in green down here or the shadow, just the length of this, how that one's changing. Turns out it doesn't actually matter. It all moves the same way. But we're going to keep going with this problem. Let's get rid of that. I don't want all that junk in there. There we go. We're going to be moving in this direction. So now I hope that we can see that we might be dealing with the idea of similar triangles. We want to know this entire thing, our z, right? This entire length. We'll create a triangle. So let's go aside and let me show you what I mean by this. Well, we have the 15 right there. 15. And then we have our entire length z. If we just go all the way to where that shadow would be. And then we have some sort of hypotenuse and we just disconnect it. Alright, cool. We got that triangle. And then we have the smaller one that's inside of it, right? So this is in the same red. This is gonna be just a little fiber, huh? Just a little fiber, just like the chimp is. And now I'm gonna make this one orange down here. And then we still have just that part of that length, but these lengths in yellow are gonna be different, of course, right? We actually don't give a shit about those yellows. We're only gonna care about our 2 values I have in there, the 15 and the z, and the 5, and what's gonna go in for the green. So let's think about this. What are we going to label the green? I've left that one blank. Now it's easier for us to think about, like, let's say that you would just walk 3 miles. but you have to actually get to 5 miles. What's left? How much further would you have to go? If you've already walked 3, but you got to get to 5. That's 2, right? We know that, but change it to variables. Isn't 2 5 minus 3? Wouldn't that be in green? Wouldn't that be the 5 minus 3? So instead of doing that, why don't we just go and say that this is going to be z minus x. Yeah? And then once we have this, we're off and running. You know? We got this, z minus x. And now we can use the idea of similar triangles. So let's do, I don't know, z over 15 is to, what's the other one? It's so z over 15. So that means I got to do that z minus x thing. And I'm done with this silly color coding bullshit. And then we'll be over 5. All right, cool. So we're gonna we wanted to set up some sort of relation. That's why we did it. We drew a picture, and then we're trying to figure out. We knew which rates we were looking for. We know what we're doing. We're trying to find that dz dt, this entire change from down here. And now we have some sort of relation up in the top right, which means if we can set this thing up in a nice way, maybe we just take a derivative on this sucker, we plug some values in, we might find out something pretty interesting. Because everything's in terms of z's and x, and we want to know what that change in z with respect to t is going to be. And we got z's up there, it's just in 2 different spots. So let's do a little bit of algebra. Let's do some cross multiplication, get this stuff out. It would actually be nicer if you just multiply everything by 15. Yeah, let's not. You know what I mean? Let's just multiply everything by 15. Why am I being silly like that? Let's just multiply by 15. And we bring that through. There's my dogs in the background. They're always awesome like that. So, like I said, no more color coding. Let's get done with that. We're going to say the 15 comes in there and we get z. And then the 15 and that's going to leave us 3. So we get 3 times z minus x. Let's distribute it in. Z is equal to 3z minus, wow, come on, bro. Come on, you're better than that. I know you are. Minus 3x. Now let's get everything over like opposite sides, stuff like that. Subtract our 3z over. Now we have negative 2z is equal to negative 3x. Nobody wants negatives. Multiply both sides by negative 1. 2z equals 3x. Hell yeah, we got a relation going here. I think we're ready to go. We have a relation. That means take a dang derivative, maybe plug in the when. Remember the when? Dude, that chimp's going to be 17 feet away, so don't forget the when. Shit, let's go take a derivative now. So we take a derivative on 2z, and we're going to get 2 times, dz dt. Yeah, that's what we're looking for. And then we go to take a derivative on our 3x, and we're going to get 3 times, and then we're going to get our dx dt. And we already know that value, so that's good news. Beautiful. Well, let's just do a little bit of algebra and find out that we, oh, no, let's plug it in first, right? Oh, no, come back. All right, do a little bit of algebra. Divide out the 2, and we find out that dz dt is merely equal to 3 halves of whatever dx dt is. And dx dt from up above, well, shoot, that was equal to 2. So we plug it on in. We do a little hiya, they go away, and we find out that our dz dt is equal to 3. 3 watts. We gotta go look at our units. All right, what were our units? Our units were feet per second. So we go back to our feet per second. We're like 3 feet per second right there. But let's go to our problem and go, hey, we just figured it out. dz dt is equal to 3 feet per second. And I'm writing it here just so we could see, we never used the when. It didn't actually matter how far away she was. It makes no difference because of the proportionality that's going on here. It wouldn't make a difference if she was 20 feet away or whether she was 5 feet away. We would have continued to have the same thing, and this would have been linear due to the relation.